Hello, I'm Caleb Cross, and this is my 9.3 distinction task. This is the CPU. Now this might look complicated at first, but today we're going to break down what each line means, what each shape means, and what instruction in M, etc. means. Now let's zoom out a bit. This is a very abstract view of the hat computer, and its different parts. So you can see we've got the CPU, and the CPU interacts with the instruction memory and the data memory, and they all take an input, and they output something. We'll zoom in a bit more. Here's the CPU, and its interface is as follows. There's a 16-bit word called in M, and that's its input. It's got a 16-bit width word called instruction, and it's got a 1-bit width word called reset. And reset just resets the program counter. It's got a 16-bit width output word called out M. It's got a 1-bit width output called write M. It's got a 15-bit width output called address M, and it's got a 15-bit width output called PC, and that stands for program counter. Let's try to say that 5 times fast. Now, how's this been translated into HDL? Well, the inputs have been specified with an in, and then it has been given its name, in M, and then in brackets, it has the word width value. The same can be said for the outputs, except it has been specified with an out. Now let's dissect this line by line. Alright, so in our chip called CPU, we have our inputs, our outputs, and now we have our parts, and this is just what comprises the CPU. Our first two lines are both NOT gates. Now you can think of this like a boolean. If instruction 15 is set to 1, then not instruction 15 would have to be 0. This just says if it is a C instruction, then a not C instruction would be an A instruction. And if it is an A instruction, then a not A instruction, or not an A instruction, is a C instruction. Now you might think, I thought this was a 16-bit width word, why are we looking at the 15th bit? Well, these values actually start at 0. And the other confusing bit is they're counted from the right. So, starting at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If you recall from the slides, the first digit in a C instruction, or in an instruction in general, determines whether it's a C instruction or an A instruction. Now, keeping that same logic, when you see something like this is referring to the fifth from the right, starting at 0. And this AND gate just says if it's a C instruction, and this is 1, then you'll be storing in the A register, because D1, or the destination 1 bit, will be 1. As you can see, 0, 1, 2, 3, 4, 5. The D1 value, if it's D1, you're accessing the A register. Now in the mux16, with 16 being referred to as how many bits wide it can take, and mux meaning multiplexer, it takes an instruction, the ALU output, and the cell value is whether or not it's coming from the ALU. So, if it is coming from the ALU, then the output of this multiplexer line will be the value that has been received from the ALU, and if it's not, then it'll just be the instruction. So, if we go to the original diagram I showed you before, and we look at this multiplexer, we can see it takes an instruction. It also takes an instruction from over here, which is the ALU's output. So the ALU output comes, and it comes in the multiplexer, and over here is our cell value. So if cell is 1, then this multiplexer value will be outputted as the ALU output value. And if not, the multiplexer will output the original instruction, but either way, they're going into the A register. Now this OR gate just says, if you're taking the A instruction, or you're taking the output from the ALU to A, either way, you're dealing with an A instruction, so you've got to load A. If load is set to 1, coming from the previous OR gate, then it will output the A register's new value. If it was set to 0, it will just output the current stored register value. Now our next multiplexer is going to determine whether our A value is 0 or 1. But when we're talking about our A value, we're talking about the lowercase a, which in the C instruction specifications determines whether we're using the A's or the M's, whether we're using an A register in our computation or an M register. So, 12th from the right, starting at 0, it'll lead here. You can pause and count if you want, but I already did the hard work. So, this will just output AM out, meaning you're either outputting an M value or an A value. In this AND gate, we're just checking again for our destination bits, whether we're going to load D, whether D is going to be 0. Here. Now, this may be confusing, it says AMD here, but D, 0, 1, 0, D is this D2 bit. So, if the fourth instruction value is going to be true, or it's going to be 1, then load D. And into the D register, take the ALU output, load if the destination value is 1, and then output it. So, as we can see here, the ALU output, as well as going to this multiplexer which feeds into the A, it splits off and it can also go into the D value. Okay, so it goes there, and then from the D, it goes back into the ALU, which, spoiler, that's our next line. Now, I've broken this down into a series of lines, and I find it just a bit easier to explain this way. So, our first input is the D out, and this is just, as I said before, whatever's stored in here just gets outputted into the ALU. The Y input is just the AM out, so whether you're dealing with an A or an M from this multiplexer, that's set into this ALU. And then these are just your control bits, C1 through C6. And over here, as you can see, they just specify what computation you're going to do, and whether you're using, again, A equals 0, you'll be using this stuff, or if A is 1, you're using this stuff. And it's as simple as that, really. Its outputs, it will output the ALU output, which is just the computation value, and then ZR out means 0 out, and NG out just means negative out. So, in this OR gate, it's initially set to false, or its first input is set to false, its second input is the A out, and it just says if A out is true, if there's an A output, then output it at this address. So this statement can only output if A out is true. Our next line, we've done a similar thing. We've set A to false initially, and then our ALU output, if that's true, then output it at out M, which if we go back here, out M goes straight out. Now, if you're using a C instruction, and the instruction value 3, yep, you guessed it, this is another destination bit calculation. However, we're going to output it as right M this time. Here, M001, that is 0, 1, 2, 3, D3, and that will output as right M. For our jump bits, if you have a output that's 0 and instruction 1, so jump 2, which is this bit, if this bit is true, then you're outputting jump equals, that's what the EQ stands for. So if jump equals 0, then jump. If you're outputting a negative number and the J1 value is true, then you're jumping if less than 0. So J1, jump if less than 0. In an OR gate, we have our 0 out and our negative out values, and if our output is 0 or negative, then this OR gate will be true and it will output 0 or negative. If our value is 0 or negative, well, the opposite, so if it isn't 0 or negative, it would have to be positive. And if it is positive, and its J3 is true, or instruction value 0, then it would have to be greater than 0. That's what JGT stands for. That's because if it's not 0, and it's not a negative number, it has to be greater than 0. If it is equal to 0, or less than 0, well then it would have to be less than or equal to 0. So this statement, if it is less than or equal to, or greater than, then you are jumping. Now this might be a bit confusing, so let me bring up my C instruction PNG. As you can see, if it is greater than, it is 0, 0, 1. So J3 is 1. If it is less than, it is 1, 1, 0. That means, for this OR statement to be true, there just has to be a bit somewhere in J1 through 3 that is equal to 1. If none of your jump values are equal, so if J1 is 0, J2 is 0, J3 is 0, then this OR statement won't output jump to A. It couldn't. There's no 1s, so it wouldn't jump. In the AND statement, if it's a C instruction and you're jumping, then load the new address into the program counter to tell it where to progress to. If you're not loading a value into the progress counter, then you're incrementing. It just means you will plus 1 to the program counter and go on to the next line, as you don't have to tell it anywhere in particular to go. Okay, our final line, the PC or the program counter. If we go back to our diagram, it gets the A instruction value, it gets the reset bit, it gets a load value, and then it will output something. Now, this reset value will reset the program counter back to 0. If this is 1, it will reset. The A instruction is being input, and the load is the program counter load. The output will just be the address that it's going to progress to. So if this is true, that means it is not going to load. So that just means it's just going to increment to the next instruction. It hasn't been told anything special, it's just going to do what it usually does. But if this isn't true, and the load is true, then it will instead load a instruction that it will have to go to, and in that case, it will go to that instruction, and then keep on going about its business. Well, I hope I made things clear for you, and I hope you can understand this now. I hope it doesn't look like gibberish, just like it did it initially, and I hope you learned something. Thank you.